Welcome back, students, to another class of Basics of Mechanical Engineering. We will continue our journey into understanding thermodynamics. So, in the last class, what we did is that we understood the concepts of the first law and how it came about, what are its requirements, and its history. Today, we will explore a few more concepts. So, in the last class, I talked about a concept called enthalpy. I mentioned enthalpy to be a combination property of internal energy plus pressure energy. Okay, so we call enthalpy a combination property of internal energy and pressure energy. So when we consider any gas or any substance, we describe its energy state by its internal energy, or we consider its energy level by its internal energy. So what is internal energy? It's nothing but the sum of all of these microscopic uh, forms of energy. So if you're talking about a molecule, you're talking about its kinetic energy in different axes, its bond energy, and all of these. Some of these energies will be termed as internal energy. Okay, and the total internal energy held by each of these molecules will be summed up, and this is the energy level held by the gas. However, what happens is that we do not consider the effort taken by the gas to exist within the volume that it is in. Okay, so for example, we have the gas around in our surroundings. What is happening is that the internal energy of the specific molecule may be a certain level. But however, once we start considering all of the interaction of these molecules in many of these molecules and what impact it will have, what we realize is that the effort taken by the molecules to simply exist within this entire space is not being considered. That is the pressure energy that the gas is exerting, the energy which is contained within the pressure of the gas, that is not being considered. Adding this up gives us a new term called enthalpy. All right. So enthalpy, as I've just mentioned, is the summation. It's a combination property of internal energy and pressure energy. Internal energy is given by the letter U, and pressure energy is P into V, pressure into volume. Okay. Now enthalpy, it is a summation of two energies, pressure energy and internal energy. It too has the same unit, that is joules. It is denoted by the letter H. So we have got H is equal to U plus PV. And if you're considering specific enthalpy, that is enthalpy per unit kg of whatever substance that you are measuring of, it is small h is equal to small u plus capital P, since pressure is an intrinsic property, into small v, that is specific volume. Okay, so these are the two equations by which we can express the value of enthalpy. All right, and naturally, since it's an energy, it is a state function. A state function being a function whose value depends on its position and not on its path. So it is not a path function, it is a state function. All right. Enthalpy, as I've just mentioned, it is H is equal to U plus PV. Now, internal energy cannot be measured directly. However, change in internal energy can be measured. Similar concept is applied for enthalpy. We cannot measure the enthalpy value directly for any particular state. However, what we can do is we can measure the change in enthalpy. Think of it this way, that in space, in the deep darkness of space outside the solar system, you can probably, it's very difficult for you to judge where exactly you may be. However, if you start moving, you will be able to roughly calculate how much you have moved. Similar principle is for enthalpy. It is very, very difficult for us to measure accurately all of the summations of different internal energies. Okay, so for us to measure enthalpy, it is very, very difficult and almost impossible. But what we can measure is the change in enthalpy. All right. So as mentioned on the screen in front of you, enthalpy values for specific substances cannot be measured directly. Only enthalpy changes for chemical or physical processes can be determined. For processes that take place at constant pressure, a common condition in many chemical and physical processes, the enthalpy change is H is equal to du, dH is equal to du, that is delta H, that is a change in enthalpy is equal to change in internal energy plus pressure into change in volume. Okay, so we utilize this form or another form of this equation, dH is equal to du plus PBV, and you can recognize this term as the work done in the process. So it is the change in internal energy plus the PdV work which is done in the process. All right, so I really hope that you have understood the concept of enthalpy. Think of enthalpy as the energy, total energy content of the system. However, please remember the genuine or the real definition of enthalpy, that it being a combination property of pressure energy and internal energy. All right, moving on, we are going to be looking at a few more concepts. Okay, so this is something that is really, really important. It is latent heat and sensible heat. Latent heat and sensible heat. Let us consider some ice. We have ice probably at your homes, in your refrigerators at your homes, or whenever you, if you're out and about in a party or something like that, and you want your cold drink or whatever drink you have to be cold, so you will ask for some ice. So let's consider that you have some ice with you, and let's study its state or its variation with temperature as you start warming it up. So what we are doing is that we are taking a block of ice and we start warming it up. Okay, and what we are doing is that in the process of warming, we are measuring how much heat we are adding, as well as the corresponding rise in temperature, and we are going to plot this out. So as what I've mentioned before, we take a block of ice and we start heating it up. Okay, so we are heating this up, and what we are doing is that we are measuring the temperature of the ice as a function of the heat supplied to it. So temperature versus the heat supplied to the entire block of ice. Now, as the ice is starting to heat up, let's say the ice is at something like minus 20 degrees Celsius. What's going to happen is that as the ice heats up, its temperature, or as you're supplying heat, its temperature starts rising. So you will have some rise in temperature as you start increasing the amount of heat that is being added. So as the ice is being heated, the temperature is also rising. So it rises till about 0 degrees Celsius. Now at this point, what's going to happen is that if you continue warming this block of ice up, it's going to start to melt. And we know that ice melts at 0 degrees Celsius. So what's going to happen is that now there's going to be a phase change in this block of ice. So whatever heat that you're adding into this block of ice is going to be absorbed by the block of ice, and it's going to be used to break those really strong bonds between the molecules of the ice, and they're going to start moving relative to one another. That is, the ice is going to change its phase from ice to water, and at this point, all of the energy is now going to be used to just change the phase, and the temperature is going to be constant. You're probably aware of this. So as the phase change occurs, the temperature remains constant. And now you're going to utilize this amount of energy from this point till this point entirely to just melt this block of ice. So at this point of time, now you're melting it. Okay, so now you're melting it. And now you are left with water at 0 degrees Celsius. Okay, so once you have heated this up, what's happened is that the ice has changed its phase from 0 degrees or from 0 degrees ice to 0 degrees water. All right, and the entire heat that you have added into the system, into this block of ice, has been entirely used up by the block of ice simply to change its phase. The temperature remains the same. All right, so now this bit is this flat bit, your temperature is remaining the same, and it's about 0 degrees Celsius. We started with -20 and now you're ending up at 0. We heat it up further, we heat up the system further. Okay, now what's happening is that your water is starting heating it up, is being heated up. So again, your temperature starts rising, 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 and to what extent? We are just keep on adding heat into this pool of water that we have. And soon what happens is that we hit the 100-degree mark. 100 degrees. Now, what happens at 100 degrees? So now we have water at 100 degrees Celsius. What happens at 100 degrees to water? It starts boiling. The water again starts changing its phase from water, that is liquid form, to steam, that is in vapor form. So now this is again a constant temperature process where all of the energy that you're inputting into the system, into this pool of water, is being used to break the bonds between the individual molecules of water and convert them from a liquid phase to a vapor phase. So now what's happening is that water is being converted from 100 degrees liquid to 100 degrees vapor. Okay, so right now you have got water converting from 100 degrees liquid to 100 degrees vapor at constant temperature. So whatever heat that you have added has been just being used to convert its liquid form to a vapor form, that is water to steam. And now if you heat this expanse of steam further, what's going to happen is that the temperature keeps on rising once more. So if you look at this diagram, you realize that there are two distinct regions. You have the region here and here, and the regions here, where I've just marked with these dots. And just let us label this as 1 and 2. I'm aware that these are separate regions where you have got ice, then water, then water and ice, then just water, then water and steam, and then the steam. Okay, so but I'm just calling it in terms of how, I'm just classifying it in terms of where when you added heat, the temperature rose, and when you added heat, the temperature remained constant. So in you've got this sort of region 1 here. Again, your region 2 here, and back to region 1 here. So in region 1, wherever you have the 1 here, whatever happened, whenever you added heat, temperature increased, and 2, when you added heat, temperature remained constant, but phase changed. All right. So you distinctly have these two regions. One in which whenever you heated up the substance, the temperature increased, and 2, when you heated up the substance, the temperature remained the same. However, the phase changed either from solid to liquid or liquid to gas or vapor in this case. The heating that you have done in 1 is called sensible heating. So one is called sensible heating and two is called latent heating. Okay, so you have these two distinct regions, 1 and 2. 1 is sensible heating where you add heat and the temperature rises. 2 is latent heating where you add heat and the substance changes its phase from one phase to the other, solid to liquid or liquid to vapor. Now, when you have the conversion of substance from solid phase to liquid phase, what we call it is the process of fusion. And when you have the conversion of liquid phase to vapor phase, it is called vaporization. All right, so you have got two distinct types of latent heating: latent heating during fusion and latent heating during vaporization. And the amount of heat that you need to add for melting a substance is called latent heat of fusion. All right, and the amount of substance that you need to add to convert it from liquid phase to vapor phase is called latent heat of vaporization. So you have latent heat of fusion, that is in this case given by, just a second, I'll just change the color here, this amount of heat, that is the amount of heat that you required in this region. And then you have got your latent heat of vaporization, which is given by, I'll just change the color again, this bit. Okay. All right. So I hope that you have understood the concept of latent heat of fusion. And the latent heat of fusion is denoted by the letter L with a suffix F. Latent heat of vaporization is given by the letter L with a suffix V. All right. So latent heat of fusion, again, let me say, is the amount of heat required to change phase from solid to liquid. And the latent heat of vaporization is the amount of heat required to change phase from liquid to vapor. I hope these two concepts are really clear. These two terms are really clear. Now, since we are talking about heat in this case, latent heat is measured in joules. However, what happens is that this is measured in the amount of heat per unit substance. So it is specific latent heat and it's given as joules per kg. So it's a specific quantity and the values of LF and LV are generally given as joules per kg. And the total amount of heat will be just equal to Q into M, that is the mass of the amount that you're trying to melt, into LF, that is, this is going to be equal to the amount of heat that is required to melt M amount of mass from melt M amount of mass. And similarly, the amount of heat required to boil that M amount of mass will be equal to M into LV. I hope with this that you all have completely understood the concepts of latent heat of fusion, latent heat of vaporization, and also the concept of sensible heat. Next, what we are going to look at is the second part, or the part where when we heated it up, the temperature of the substance changed. Okay, that is sensible heating. Speaking of sensible heating, we need to talk about a term called specific heat. Okay, so as I had mentioned earlier, the temperature and amount of heat that is you're adding it into the substance when you are trying to melt it. What's going to happen is that the temperature first rises, then it starts melting, then it again rises, then it starts boiling, then it again starts rising. Yes, so we recognize this graph from earlier. This part is your latent heat, and this part here and here, this part is again latent heat, and here the three x's are this is where your sensible heating is taking place, wherein when you add heat the temperature rises. Now what we come across is a specific relation between how much heat that you add into a substance and how much temperature that the corresponding increase in the temperature. So this is determined or this varies from substance to substance. So if you add a unit amount of heat into, say, a block of wood, and you add the same amount of same unit heat into a block of metal, you'll realize that the temperature change is different. Okay, so because of that, we need to define a parameter called specific heat. Now, specific heat is nothing but the amount of heat that we add per unit mass of the substance to raise its temperature by 1 degree Celsius. It is, again, let me repeat, it is the amount of heat that you add per unit mass. So it's the amount of heat that you add to 1 unit of mass, or of the whichever substance that you're trying to warm up, and its temperature rises by 1 degree Celsius. All right, so you have this equation Q is equal to mc dt, where C is your specific heat capacity. Okay, so you have got this equation, and finally if you just rearrange, you will find that C is equal to Q divided by M into delta T. This formula, however, is applicable to liquids and solids. So you have something called a specific heat which you get once you do this operation. So what you do is that you take a unit mass of whatever you want. Say you have a unit mass of say a block of metal, and you take unit mass means 1 kg. So you take a block of 1 kg of metal and you start heating it up. You start heating up and you measure this amount of heat that you're putting in. And the moment the temperature rises by 1 degree Celsius, the amount of heat that you got is nothing but a latent heat capacity. The latent heat capacity again is given by the letter C. All right. So it's denoted by the letter C, and its value is given by the units joules per kg Kelvin. All right. Sometimes we also measure it in terms of kilojoules per kg Kelvin. All right. However, what happens is that in the case of gases, when you do this measurement, you come up with a problem. If you maintain the pressure of the gas as constant, you will get one value. And if you keep the volume of the gas as constant, you will get a different value. So what's happening in the case of gases? If you take 1 kg of gas, I have a box, I take 1 kg of gas, and you try heating it up, and I kept the volume as constant, I will get one value of the specific heat capacity. However, if I put it in a piston cylinder mechanism and I kept the pressure constant, by if you'll recall, the last time we tried to keep pressure constant, we just kept a mass, some mass there. So since the mass was the same at all positions, the pressure which is being exerted onto the gas is also constant. So now what we have a piston cylinder mechanism. You have got gas trapped inside it. You have got 1 kg of gas trapped inside it. And what's happening is that the moment you start heating it up, what's going to happen is that you get a different value of specific heat. And what you find out is that this C2 is greater than C1. That is the amount of heat that you require to raise the temperature in a constant pressure process is greater than the amount of heat required to raise the temperature by 1 degree Celsius in a constant volume process. This is nothing. This is nothing that is really to be sweated about, because this is a property of the gases. Where if you measure this the specific heat at constant pressure, you will get one value, and if you measure the specific heat at constant volume, you'll get a different value. So you denote the C1 as that is specific heat at constant pressure as CV. All right, and you denote the specific heat as measured in at constant pressure as Cp. All right, so you for gases you have got two specific heats. You have got Cp and Cv, and Cp is always greater than Cv. Okay, so this is a really important property of gases, and I really hope that you all try to remember. So you have got two values of specific heat for gases, a single value for liquids and a single value for solids. Okay, so let us explore why this happens. Why do you have this two values for Cp and Cv, and how this translates into what exactly are you measuring? So again, let us consider the two scenarios for gases, that you have a box, a closed vessel in which you have got gas and you're heating it up. You're heating this gas up. Okay, and again you have got your piston cylinder mechanism, where you have got your piston fitted into a cylinder and you have got a known mass exerting a constant pressure, and you have got the same gas. See, this is again also 1 kg, and this amount of gas is also 1 kg, and again you're heating this gas up as well. Now, what exactly happens in this process? As soon as you start introducing heat into this, or thermal energy into the gas, what happens on a molecular level is that these gases or these molecules start vibrating even more. They start moving more. Translation, rotation, so on and so forth. Probably the bonds even get energized. What is this? What is this microscopic increase in the energy levels? This is nothing but the increase in its internal energy. So when you are heating this gas up in a closed environment, in a constant volume environment, when you added the energy into the system, what you did is that you increased its internal energy. Okay, so whatever heat that you added increase its internal energy of the gas. Let us look at the second scenario. Here what happened is that you had the molecule, and as soon as you started heating it up, its kinetic energies along different axes started increasing. Am I right? It's translational, rotational, etc. However, this gas started pushing against the movable screen. Now in the first scenario, once you started heating it up, if you realize that once you start heating up a box or a vessel, an enclosed vessel, what happens? The pressure inside rises. So the gas did not allow, the vessel did not allow the gas to push it open. It was, since the vessel was rigid, the gas remained at a constant volume. Its volume did not increase. However, that is not true in the second case. What is happening is that you are using this the increased energy level to exert a bit more pressure on the sides of the container. Now this causes the container to start moving upwards, the piston to move upwards. So it started increasing its volume. As soon as the volume increased, the pressure equalized. Okay, so as soon as the pressure equalized, what was happening is that you have moved a bit. Okay, so you increase the internal energy, but you at the same time you did some amount of work where you pushed this mass up by a little. And if you remember, so you have got change in internal energy plus PdV work. And what is this? This is nothing but change in enthalpy. So when you heat a substance at constant volume, what you're doing is that you're increasing its internal energy. And when you heat a substance at constant pressure, what you're doing is that you're increasing its enthalpy. Okay? All right. Using this, what we are going to do is that we are going to look at a sort of a different way of expressing Cp and Cv. So Cv is nothing but du by dt, that is change in internal energy upon change in temperature at constant volume, and Cp is change in enthalpy upon change in temperature at constant pressure. Okay, so this is the way we express Cp and Cv for gases. Let us look at this concept a bit more further. So you have got specific heat at constant volume. Mathematically, as I've just mentioned, you have got this, that is Cv is equal to du. Now this is a way of writing partial derivatives. I'm sure you'll know this from your other classes. Du upon dt at constant volume. Now what we are going to do is that we are going to look at the first law of thermodynamics. So you look at the first equation wherein Q minus W is equal to change in internal energy. If you write it in a differential form, you have got dq minus dw is equal to du. That is difference of heat transfer across the boundary minus the work transfer, work done on the system or by the system, is equal to the change in internal energy. Now, what we have again is let's just rearrange this equation and we'll try to get du plus dw. Okay, so now you have got this expression of heat is equal to internal energy plus work done. However, we know that for an constant pressure, constant volume process or an isochoric process, the work done is equal to 0. So if we plug in that value or plug in the condition there, what we are left with is dq is equal to du. dq is equal to du. All right. And again, if you utilize this equation, you have got Q, that is the heat supplied at constant volume, is equal to mCv dt, or in specific form where you want to write specific heat, so you'll be Cv dt. Okay, so this is the expression for specific heat or heating at constant volume. Next, we are going to look at the second condition, that is heating at constant pressure, specific heat at constant pressure. So again, we have got our equation. What we are going to do is that Cp is equal to dou. This is called partial differential, and you instead of d, we call it dou H upon dou T at constant pressure. Applying the first law, Q minus W is equal to delta U. If you write in differential form, dq minus dw is equal to du. Okay. All right. Now, what kind of work are we doing here? We are doing PdV work. So we just substitute that here. So Q minus PdV is equal to du. Now let's express the definition or the mathematical expression for enthalpy. H is equal to U plus PV. Now if you differentiate this on both sides, you are going to have dH is equal to du plus d into a differential of PV. If you open this up and follow the chain rule, you have got dH is equal to du plus PdV plus VdP. Okay, so you have got this expression. Now you notice that this is PdV plus VdP. For a constant pressure process, change in pressure is equal to 0. So what you are left with is, if I'll write it here down here, dH is equal to du plus PdV, because this VdP term turns to 0. Okay, now again I'll write this equation here, dq is equal to du plus PdV, and so you have got dq at constant pressure is equal to dH. That is, all the heat that you added at constant pressure was used to increase the enthalpy of the system. And previously, whatever heat that you added at constant volume was used to increase the internal energy of the system. So this is a definite proof. This is a mathematical proof which says that, which proves the statement that we made earlier. That is, if you increase if you add heat at constant volume, what is going to happen is that your internal energy changes, and if you add heat at constant pressure, your enthalpy of the system changes. With that, I will bring this session to a close. I really hope that you have taken the time to understand the concepts which are covered today. I will see you in the next class.